and I'm going to talk about it. I screwed it up is the way I'm going to talk about it. I'm going to talk about it in terms of all of the chemistry and geology leading up to what beryl is, and then talk about the gem varieties. So I'm going to cheat a little bit and not just go to the pretty part. I'm going to not get very technical, although there are going to be a lot of strange words that are used in very different fields along the way. So that's what I'm going to talk about. And I'm going to start with some simple definitions because most people know that there are minerals and rocks, but not what the formal definitions are, or that there's an international mineralogical association that has the last word on what's a mineral and what's not a mineral. In any event, there are really two parts to the definition. One is that it's a substance with a single chemical formula, like sodium chloride, NaCl, or CaCO3, calcium carbonate. But in terms that we're going to be using, it's an inorganic solid with a specific crystalline structure, because without that crystalline structure, it can't be a gem. And so typical minerals are aluminum oxide or corundum, and that's what sapphires and rubies are, and beryl, that funny long formula, a little more complicated than the simple one for corundum. And the other thing that's a little different than people expect is you can have the same formula, but if that material has a different structure, then it's a different mineral. And so for calcium carbonate, there's the beta form, which is calcite, there's the lambda form, which is aragonite, and there's the mu form, which is vaterite. And so there are really three different minerals, all of which have the same calcium carbonate formula. So that's a little more complicated than people expect. On the other hand, rocks are simple. They're just a mixture of minerals. And so people know what granite, and around here what basalt is. And most people have also seen limestone, like the stuff in caves. And I'm not going to talk about rocks specifically very much. On the other hand, when you get to the word gem, that's really doesn't have a definition in geology. That's really a choice based on an individual's idea of beauty. So it's any material that's used as human decoration or jewelry. And it can be a mineral, it can be an organic substance like amber, and there are even some rocks like gabbro that are used still today as or in jewelry. And there are really about 200 substances on most lists. Now, beauty is again a sort of subjective idea, but when you start talking about jewelry, you're almost always talking about color. You want something that people will notice. And on occasion, you can talk about sparkle fire, although that's more of a diamond thing than most other gems. And I don't really like diamonds very much, except colored ones. Okay, so the next thing is that very few minerals occur as large, transparent single crystals. And that's what you need to cut a gemstone into what we call a gem. And so by that criteria, 50% or more of all gem materials are silicates. And that's why I'm going to focus on silicates. And in addition, there are practical considerations. There's durability. I mean, if the stuff crumbles when you touch it or look at it, it's not very useful. And there's also the issue of rarity. If there isn't enough of it to sell, for example, then there's really no gem market. And so if you add that criteria, only about 70 minerals get to be gems. And of those, only about 20 are considered A-list gems, the ones that most people know the names of, precious ones like emerald and ruby and diamond, and all the others that people know that are called semi-precious, but in a lot of cases are a lot rarer than the ones that people call precious, especially diamonds. Now, of that A-list, 13 are silicates. So silicates are even more important when we start talking about gem varieties. And there's actually a B list, which is sometimes used in jewelry. And for nuts like me, there's a C list and a D list. And so I've got lots and lots of examples of all of those last three categories as cut gems. So let's take a step back and start talking about where silicates come from. So this is a quadrant of the Earth. And you can see there's different layers, and the ones we're going to concentrate on are up at the top. That purple one in particular, but also the green one and that little tiny brown one. Those are the lower mantle, the upper mantle, and the crust. And the lower mantle is a real viscous liquid. And that's what the tectonic plates float on. The upper mantle is pretty thick and it's solid rock, but it's very unusual rock because it's very hot and it's under very high pressure. And finally, there's the crust, which extends under the ocean. And if you go down to the bottom of the deepest trench or up to the top of the highest mountain, you get a range of thicknesses from about 5 miles to about 30 miles. So really, really not very thick. Now, the lower and the upper mantle are about 95% silicates. So again, that's why silicates are important. And surprisingly, the mantle contains basically 8 elements, the ones listed. And all the other elements together constitute only about 1%. And the silicates, even though there's lots of them in the mantles, they're just 4 main types: olivine, garnet, orthopyroxenes, and clinopyroxenes. And the last 2 are sort of generic categories, and the specific in each one is either a magnesium-rich compound called enstatite, which you can actually find as a mineral that can be cut, but it's an ugly brown, so nobody cares. And then there is augite, which has calcium as well as magnesium as part of its formula. And it's really not a single compound. It's a mixture of compounds. Anyhow, now let's look at the Earth's crust. And what we see is that the elements in the crust are the same as the ones in the mantle. And so there we've got a red arrow saying all the other metals and non-metals that aren't in that big list only constitute about 1.2%. And you can see that silicon and oxygen are the 2 most abundant elements. So again, that are silicates, which are made up of silicon and oxygen. In any event, the Earth's crust is more than 92% volcanic, igneous rock. And you can see in red the three categories of rocks that you learned about probably in grade school: igneous, sedimentary, and metamorphic. The point of the last couple of lines is all of those types of rock are very, very rich in silicates, much more than 92%, with a couple of traces of a bunch of other things. And so as a result, the Earth's crust is more than 85% silicates. Why is that? Well, volcanic action originates in the lower mantle, and it comes up through the upper mantle and deposits molten lava, either on top of the Earth's crust, so that's a volcano, and that's called extrusive magma. And the important word's extrusive, but most of the time the lava never reaches the surface and gets deposited in either big domes or in those long stringy things, which we'll talk about in a minute. And that's called intrusive magma. It never sees the light of day. And so that's why the crust looks like the mantle, because it is the mantle. That's where it came from. Now you can actually find the unchanged silicates of the magma in the crust. And so you've got olivine and garnet and orthopyroxene and clinopyroxene, and those are the places where they can be found. And we're talking about on the surface for the most part, like the beach sand, or just sitting around in a big cliff in the Colorado Plateau. But most of the time, the magma silicates, as they solidify, undergo structural and chemical transformations. And that process is called differentiation. And so there's really two types of silicates in that case. What are called mafic silicates solidify at high temperatures. And so they're nearly the same as the ones in the mantle. They're undifferentiated for the most part. But the interesting thing about them is that they contain mostly the heavy elements, magnesium, iron, and calcium in the list that I showed. On the other side of the spectrum are the felsic silicates, and they solidify at lower temperatures. And so along the way, they become the products of differentiation. And for the most part, they contain the light elements of those 8 that aren't in the ones that are in the mafic silicates. And just for fun, it's interesting that the minerals that solidify at like temperatures combine to form rocks. And so combining to form rocks is not just arbitrary. It's a function of the temperature at which the minerals in those rocks were formed. Now, this is the process of differentiation that I was talking about. It's called Bowen's reaction series. So you've got high temperatures on the left that are the first to crystallize and low temperatures at the bottom. And on the other side, you have the different kinds of rocks that are formed at all of these different temperatures. And so you start out with olivine, and that one sort of precipitates out first, and then pyroxenes, and then amphiboles, and then a form of mica, which wasn't present in the mantle silicates. And all of these other ones at the bottom. At the very bottom is quartz. And on the other side, the calcium-rich ones come along. And by the time you get to the bottom, those are the sodium-rich ones. And if you look on the right side, what you see at the bottom is that the felsic rocks are granite and rhyolite. And the difference between them, besides usually their color, is that felsic ones are extrusive. Or rhyolite is the extrusive felsic. So it's found on the surface. Granite is intrusive. So it never sees the light of day until the ground over it gets weathered away or washed away by some geologic process on the surface. And then you've got all of these intermediates. And if you look at mafic on the right, you'll see gabbro. And gabbro and basalt are the same kind of thing. Gabbro's the intrusive version of the rock, and basalt is the extrusive version of the rock. So all of this is pretty simple and makes a lot of sense along the way. All right, so it turns out that even with differentiation, there are just 9 silicates in the crust. And they're shown under the 2 categories of mafic and felsic. And the new ones are in that reddish color. And the old ones, the olivine and pyroxene and the amphiboles, are in black. And what you see is there's still a touch of garnet. But garnet gets melted at the high temperatures of magma and doesn't really stay as garnet as things cool. So only traces of garnet stick around, and the elements that were in garnet get distributed in the rest of the stuff. All right, now to complicate matters a little bit more, the 9 silicates belong to just 6 different structural classes, sort of a general category. And you can see the different categories. And the thing to notice is that feldspars are by far the most abundant kind of silicate in the crust. By far, more than all the others combined. And that's a little bit unfortunate because there really aren't very many good gems that come out of feldspar. And all that says is, even though you've got all of these silicates, they're pretty rare, at least the ones that can produce gemstones. Now we got to take a step back and look at a little bit of basic silicate chemistry. So as I said, oxygen and silicon are the most abundant elements, and they readily combine to form what I've been calling silicates. The simplest silicate is just this little pyramidal looking thing called a silicate anion. One silicon surrounded by 4 oxygens. It has, each of the oxygens has an unpaired electron, and so it has a -1 charge, and it can attract a positive cation of some kind. We're not going to talk. So binding to is really ionic attraction between a positive and a negative, like in salt. Sodium's the positive cation and chloride's the negative anion. But silicon or silicates are a little unusual because one of the oxygens at the end over here can actually bind to another silicon. And so you end up with what's called a dimer. And each of the outer oxygens in the middle oxygen now has all of its extra electrons shared, but the outer oxygens still have an extra electron, so it has a -6 charge. Right? And now it gets more complicated because dimers can continue to share their outer electrons, and so you can produce chains and then these big 2-dimensional sheets. And you, since oxygens that have unpaired electrons are sticking up in the air, you can get 3-dimensional structures. And so all of this stuff is called silicate polymerization. And this is the process that happens during differentiation. And so these are the 6 silicate structural classes in the crust. You've got the simplest one, olivine, which is just the tetrahedral silicate anion. And pyroxenes are single chains of the linked silicates. Amphiboles are 2 chains stuck together. And then micas, and we saw that there were 2 kinds of micas primarily, and also clays end up being 2-dimensional sheets all linked together. And then when you get to the feldspars and the quartzes, they're 3D frameworks. It's easy to see that the feldspars can keep going in all directions in this three-dimensional interlinked framework. The quartz one's a little harder to see, and it's actually a spiral of interlinked silicates. So it's three-dimensional, but in a funny way. In any event, what we've seen is that the geography is that you go from mantle to crust and then through Bowen's reaction series, increasing silicate polymerization along the way. So that's a pretty straightforward process. Now, this is a little messy, but you really don't have to pay much attention to this. You can also describe these structural classes by their silicon-oxygen ratio. And so each of these classes has a different name, and it has a different silicon to oxygen ratio. And you can see that they're usually called orthosilicates, contain olivine and garnet. And the inosilicates, there's our single chain, and it's got the pyroxenes, and the interlinked chain is the amphiboles. And then you've got the sheets, which are the micas and the clays. And at the bottom, you've got the 3D frameworks, which are the feldspars and the quartzes. And right in the middle of all of that stuff, you've got cyclosilicates. And they're a ring structure. And they're all different sizes of rings that you can produce by linking silicate anions together. But the most common one is the six-membered ring. And I've highlighted that in red for a reason that'll be obvious in a few minutes. Now, just for completeness, these are all of the silicate minerals that are in these structural classes. And the 20 A-list gems that I was talking about are underlined. And I've really underlined them as their minerals. And there's the cyclosilicates, and beryl is a six-membered cyclosilicate, which is why it was in red before. You're not going to recognize most of the names on this list, but don't worry about it. And I'm only going to point out a couple of things in the list sort of as asides. If you look at the single and double chains, you see at the very beginning of the list is jadeite and nephrite. Those are the two forms that we call jade. And what are they? They're either long single chains or double chains, two chains linked together. So they're long fibrous strings. And that's why they're so damn hard to carve and why you can't break them and so forth. And the other one to look at is under the double chain, there's a mineral called actinolite. And there's two very closely related minerals called tremolite and rebecite. And those are the minerals that make up what we call asbestos. So there are really three different minerals. They're all these indestructible double chains, long double chains, which is why asbestos ends up coming out in these long fibers. They reflect the actual chemical structure of the mineral. And that's why it doesn't break down, because it's pretty much indestructible. Anyhow, the list is just for completeness. And if you're interested in which one's where, you can always get a copy of the slides like usual from either Don or Lou. All right, so now we're going to do a little more geology, but this is going to be what happens to the magma and the silicates that are in the magma. And we're going to talk about pegmatites, which is what we look for when we're prospecting, and that's where most silicate gemstones are found. So not diamonds, not fluorite, which aren't silicates, but most of the silicates, like beryl, which is the one we're interested in, but also topaz and tourmaline and a lot of others. That's where they come from, pegmatite. So what is it? You've got hot magma, which doesn't reach the surface. It still cracks the surrounding rocks because it's at about 2000 degrees Fahrenheit. And you put a hot magma on a cold rock and the rock cracks. And so the magma flows into the cracks and eventually it's going to harden. And so pegmatite is not a mineral, it's a formation. It's this long seam inside a different kind of rock. And more complicated, and I'll talk about it in a second, there are volatiles, like, believe it or not, water in the magma. And as the magma cools, it's in the pegmatite, and it separates and forms pockets inside the pegmatite. And the bottom shows a typical pocket. So you have the stuff around the outside, which are the minerals you expect to crystallize first. And usually they're feldspars and micas, because this is pretty close to the surface, so it's cooled a lot. And the other stuff is already precipitated out. And then at the very middle, what you end up with is a core. And in that core is where you find the beryl and the topaz and the other important silicates. But the important thing is that that core cools off very slowly. And so what happens is the rare minerals, and you'll see why topaz and beryl are rare, for example, they cool slowly, and so you end up with large crystals. So there can be beryl in all sorts of places, but the beryl we want for making gems is in those pockets for the most part. And so when you go out prospecting, and I'll show you if we get to my pictures of me, how you look for those key indicators when you're prospecting. All right, so what are pegmatites for sure? They're seams of intrusive igneous rock. Intrusive because they never reach the surface. The magma that starts to form them is under incredible pressures, more than 200,000 PSI. I mean, under those pressures, there are lots of different kinds of magma, but the ones we're interested in are the ones that have high silicate content and are non-explosive. And the reason they're non-explosive is they contain less than 4% water by weight. Usually what causes a volcano, or in this case, magma under the surface, to erupt as a volcano is because it's got too much water in it. And so as it cools, that water makes it go boom as it turns into steam. And yep, you got a volcano. And there's other stuff like carbon dioxide in those volatiles, and fluorine gas and chlorine gas and a bunch of other stuff. And so all of those end up causing a big explosion. But if you've got less than 4% water, usually the pressure can contain the magma to the point where it starts to solidify. And so once the pressure drops, all of these fluids are surrounded by solid rock and they can't go anywhere. So the fluid contains superheated water and separates to form pockets. The ions that are in that high silicate magma, they migrate and concentrate in that lower viscosity fluid inside the pocket. So the pockets become very rich in all of those less than 1%, the rare elements. So rather than just being scattered any old place, silicates and these rare elements are forced together in the pocket. And that's where you also find very large ions, which normally you wouldn't find anyplace else, like tungsten. And you also find the rare earth elements. So if you go prospecting for some of these other things, pegmatites are the way to go. In any event, as I said, the rare minerals are formed because all of those rare elements are in one concentrated place, and they wouldn't be that way anywhere else. And then because cooling is slow in those pockets, because you've got basically water around them to sort of act as a heat sink, they grow into very large crystals, where very large is relative. They can be as much as 1 to 2 inches for a good gem quality crystal. And that's pretty darn big when you think of how small an actual cut gem is. And so again, beryl and garnet and topaz and tourmaline and zircon and some others like chrysoberyl and apatite, lots and lots of the gem silicates are in those pegmatite pockets. And beryl would never have formed otherwise because it contains beryllium, which is present in basically trace amounts compared to everything else. And tourmaline contains boron, same deal. And apatite contains fluorine, same deal. And so that's the place where rare minerals like gem minerals are formed. All right, so what do these pegmatite pockets look like? Well, this is a small one in the upper picture. And there's a guy inside. The biggest ones are the kind where they drive trucks into them and they lay railroad tracks on the bottom to bring out the stuff that they're looking for. So they start looking around the edges of that pegmatite pocket, and that's where the crystals are. And they have to do it very carefully. But in the meantime, they're dragging out a lot of stuff, rocks that they don't want. Now, you don't have to have a pocket per se. So if you look at the bottom picture, that thing next to the man that's laying on the ground that's got the sharp edges, that's a beryl crystal. And some of the ones in that feldspar quarry, so they were really not looking for beryl, they were looking for all that feldspar because it has all kinds of industrial uses, even though it's not good for gems. You know, some of those were over 30 feet long, and the largest beryl crystal, and it's the largest documented crystal of any kind, came from Madagascar, and it was over 60 feet long and weighed almost 1 million pounds. That's a big crystal. Now, it's not gem quality, but it's a big crystal. All right, so one more subject before we get to what everybody's been waiting for. Where does color come from? And some more chemistry of a different kind is required this time. So there's 2 kinds of color in minerals. There's idiochromatic color, and that's intrinsic. It's because of the formula and what ions are in that formula. And so peridot is the gem form of the mineral olivine, which has that strange formula where there are 2 end members, one of them that's got only magnesium in it plus silicate, and the other one's got only iron in it plus silicate. Well, peridot is right in the middle, but more towards the end that's got mostly magnesium. So there's 15% by weight of iron. And at that point, it grows crystals that are transparent. And those crystals are green because of a really high iron in the +3 oxidation state. as part of its composition. But most gemstone minerals are actually colorless. If they're really pure, they don't have any color at all. And so the colored gemstones that are formed from those minerals are called allochromatic colored, because the color is caused by impurities that are trapped in the crystal as it grows. And you can have all sorts of impurities that produce color. You can have ionic purities, transition metal impurities like the ferric ion, and they produce color depending on something called the ligand field effect. And that's a whole, I'm an inorganic chemist, so that's one of the reasons I got interested in color and then in colored gems, because it's a perfect example of ligand field effects, and that's what I was interested in. And one of these days I can talk about some of these other things. But there's also charge transfer absorption. If you've got corundum, the aluminum is in the +3 oxidation state. Well, if some of the aluminum is replaced by titanium in the +4 oxidation state, and next to it is an iron in the +2 oxidation state, they can transfer an electron when they get hit by light energy. That's called charge transfer absorption. And that's actually what makes sapphires blue. Pretty exotic process, and you can see why blue sapphires are rare, because not only do you have to have 2 impurities, those 2 impurities have to be right next to each other as defects in the crystal as it grows. And a good sapphire has to have uniform color across the whole gem. And so that makes it even rarer. And it has to have a lot of these defects of the titanium and the iron, or the color is so pale you can't see it. So all of a sudden, the quality of a gemstone starts becoming obvious because of its rarity. And finally, you can have something very weird. You can have what's called a color center that absorbs light. And it's a hole that's created by a missing ion. And so instead of being replaced by something in the crystal, there's just a missing ion. And usually it's an anion, and they're called Fabry centers. And an electron is still there and occupies the vacated space, and it can absorb the light because it's surrounded by a bunch of other atoms, and you have sort of a mini field effect, a very strange one. All right, positive centers can do it too, but they're very complicated. I won't even try to explain those because I don't really understand them that well. In any event, if you look at gemstone minerals, here are a whole bunch of colorless ones that you're not used to seeing this way. You're used to rock crystal or quartz. You might have seen white sapphires. You might have seen white topaz. You might have seen white zircon, but I'll bet you've never seen a white garnet. It's called a leucogarnet. It's one of the rarest kind of garnets there is. And you've definitely never seen a moonstone, which is one of the few gems that are produced by feldspar. They're almost always cloudy, and they're almost always cut as a cabochon, and they've got color in them. But there's one that is colorless and has been faceted. And so those two on the bottom left and center are two of the rarest gems you will ever see. All right, now finally we get to what everybody's been waiting for. And let me check and see how we're doing on time here. Oh, that's not terrible. This will go fast because this to me is the least interesting part. In any event, there's the chemical formula for a beryl at the top. It's a very, very common mineral. You saw those giant crystals laying on the ground. And so actually, those giant crystals were mined because they were the major ore of beryllium until we found another ore that could take their place because it was richer. It's called Bertrandite, and it's all over Utah specifically, but it's loaded with beryllium compared to just a few atoms in beryl. There you see the cyclosilicate six-membered ring at the bottom that we showed before. And because of that, you end up with crystals that are hexagonal in symmetry. You connect the vertices, and those are all equal triangles, so you end up with a perfect hexagon. And so the crystals that grow are the ones on the right. And you can see at the top view in the center that the tops are hexagonal, and the whole crystal all the way down, if it's a good one, is hexagonal. But the important thing is that in order to get a gem quality crystal, that big crystal has to be transparent and inclusion and defect free. So all of the stuff around that big crack is useless. And all of the stuff towards the bottom is useless. And in order to get a good gem quality gem out of a crystal, you actually have to look at it through magnification. And that's what the 10-time magnification gem loops that gemologists and jewelers use. That's what they're all about. They're looking for defects because, as you'll see, that's what determines a good gem from a bad gem. And in the case of all of the beryls, with one exception, they have to be totally defect free. So there's another complication with beryl, and this is looking down at what's called the unit cell, how the beryls actually crystallize. And what happens is you get layers because those rings are flat. And so those rings loop together, and what you see is you've got two other kinds of molecules or atoms besides the beryl ring around the outside, but what you end up with is stacks of these rings on top of each other. And inside is a channel, and a pretty big one, almost 5 angstroms in diameter. And when you consider that most cations, the kinds that we were talking about as impurities, are less than 2 angstroms in diameter, you can see that those channels can trap metals, and they do. But most often, for sure, they trap water because water molecules fit in those channels as well. And so in order to get one of those transparent, defect-free crystals of a beryl, you end up having to have between 1% and 3% water in the crystal. If you don't have the water, the crystal cracks and it's no good. So now let's talk about gem varieties of beryl. And just like the other minerals, it has a colorless form that's called goshenite. And because none of the atoms in the beryl itself absorb light, it's colorless. And the good stuff really is beautifully colorless. It was discovered supposedly in 1844 on a farm in Massachusetts, and that's where it gets its name. But the problem is the ancient Greeks knew about it and used it to make eyeglasses because the good stuff was so transparent. And as I showed you, you can get huge beryl crystals that are colorless. But the largest inclusion-free ones, you can only cut at a maximum 30 to 40 carats worth. of a gem, and those are museum quality. Usually what you see are less than 5 carats. Now, for those of you who don't remember what a carat is a 1/5 of a gram. All right, you know how small a gram is. And so now what you have is somewhere between 6 and almost 8. I can't do arithmetic. Yeah, 8 grams of gemstone. Now, I could talk about history, I could talk about where they're found and all sorts of other things, but I'm not going to do that. But if you're interested in any of that stuff, my favorite go-to place is called mindat.org. And it has an incredible website. But I've given a bunch of links for a bunch of other websites that are pretty good, even though they're more specialized and they don't cover as many different kinds of minerals. All right, now on to one that people should recognize. Aquamarine, water of the sea. It can be anything from greenish blue, and that top crystal is more green than blue, so really bluish green, down to these bluish crystals on the bottom. And as you can see, beryl crystals that are colored with iron in 2 different oxidation states, or though in this case, 1 oxidation state because it's so blue, can be gigantic. And so the largest good crystals are about 110 kilograms. That's a big crystal, you know, that's over 220 pounds. It's about 250 pounds. But by the time you find a section that's inclusion free, so it's really completely gem quality, so you can cut it, what you end up with is still a very large gemstone. And that thing on the right is a carved obelisk that's 24 inches tall, and it's called the Dom Pedro. When you get to really big gems like the jumbo of the class or the jumbo of the variety, they almost always have names because they're so special and so rare. And so most aqua gemstones, if you find one that's over about 30 carats, you know, that's a big one. There still are a lot of bigger ones, unlike the beryl, you know, because the beryl itself, the goshenite, has to be impurity free as well as defect free. And so that's even rarer than something like an aqua crystal that can have impurities in it. And so that's why it's much bigger. In any event, now we got to take a detour again and talk about determining the value of colored gems. And I'll show you why in a second. Most people know about the 4 C's for diamonds, and these are basically the same 4 C's, but with a twist. They have a very different order and a very different order of importance in terms of the quality and the value of a gemstone. And color is the most important by far, and it's also the most complicated that I'll show you in a second. And so there are 4 properties. The color itself, is it red or is it red-green? Those are 2 different colors. Or red-purple or something like that. All right, saturation, which is a little hard to describe, but it's brightness or vividness. You can tell when you're looking at a gem, is it sort of dead looking or is it really bright? Does the light really sparkle in it? Then there's the depth of color. How blue is it? And then there's the coverage. What you want is to see the same color across a colored gemstone. Otherwise, it looks bad, right? And here we've got carat and the measure of weight. Now, carat in the case of colored gemstones is really a bad stand-in for size. Because in the case of diamonds, there's sort of a standard table where if you know that the diamond has a standard cut, like round, brilliant, like in an engagement ring, and you know how much it weighs, you know exactly how big it is looking at it from the top, at what's called the table, the flat part at the top of the stone. But that doesn't work for almost any other colored gemstone. And so what you have to do in order to really know something about that gemstone's value is measure the surface area. And it's measured in millimeters. But if all the other C's are equal, the value of a stone goes up non-linearly with size, because there are actually breaks. It goes up like stepwise. You get to a certain carat weight, and that becomes the stuff above that is more valuable. And so usually you're looking at things like 1 to 5 carats, and then there's a break, and then 5 to 10 carats, and then there's a break, and then 10 to 30 carats, and there's another break, and then it goes up exponentially as far as value is concerned. Now, I mentioned clarity, and in the case of beryl, it's all important. So it's critical. But there are other stones, including a variety of beryl, where it's pretty much unimportant. And then there are some stones where impurities in the stone actually add value to the stone. They tell you that the stone is real, it's not synthetic, number one, and they tell you where it comes from, which in certain kinds of stones is really important in terms of the assigned value. And then finally, there's the cutter's trade-off. For diamonds, it's pretty straightforward. You get a diamond, you cut it to a classical shape, which is pretty much prescribed in books, and you make it sparkle as much as you can. So you sacrifice carat weight for clarity. Absolutely not the case when you cut a colored stone. The rules are different for every single colored stone, and also for the kind of jewelry you're going to use to make with that colored stone. And so a couple of the C's are very different than in case of diamonds. So let's look at color in aquamarine. And as I said, a lot of aquamarine comes out with a greenish tint because the ocean is not pure blue. That's very unusual. It's got all kinds of impurities in it. And so the ocean usually looks like greenish blue. But in the US market, that's a no-no. And the greenish tint is from the ferric ion impurity in the beryl. And so it's heated to get rid of the ferric ion, and you end up with a blue, which is what the US market thinks is a good aqua. Now, there are a number of different kinds of aquas that have been discovered recently in Minas Gerais, which is a province of Brazil, out in the middle of the jungle where most of the mines are. And the Maxis mine was discovered in 1917. That stone on the bottom left is from the Maxis mine. And it's a pretty good aqua, really nice color. But the color is caused by color centers that were produced by natural radiation from the surrounding stone when it was formed. And so if you take the color out into sunlight or it gets too hot, the color disappears and turns yellow. So that's caused other kinds of stones to be called Maxis type, because a lot of different colored beryls are either enhanced or color formed by subjecting them to gamma or neutron radiation. And so they're not synthetic, they're not totally produced in the lab, but their color is synthetic, which gets really tricky. So Maxis type stones are really not very valuable, even though they might have beautiful color, because the color is transient. On the other hand, in about 1950, another mine was discovered in a similar region. And the stones from that mine are called Santa Marias. And they have permanent, natural, dark blue color. And they are considered the creme de la creme of aquamarine. And since the mine played out pretty quickly after it was discovered, gems are extremely rare. And so here are a couple of typical prices. For a less than 3 carat square emerald cut, you can see that the surface area and the depth of the stone are measured to the 100th of a millimeter. That stone is worth about $3,800. And so more than $1,000 a carat. On the other hand, I found a 7.7 carat pear-shaped Portuguese cut, a really fancy cut pear-shaped stone, sort of elongated. It's longer than it is wide, so it's got unusual proportions. So the cutter decided to maximize the size of the stone, because even though it's a huge stone, it's a pretty shallow stone. It's almost as shallow as the 3 carat one. But it's worth $16,500. So $2,000 a carat. And if you get a bigger Santa Maria, the prices are astronomical. Anyhow, how do you decide what's a good color for aquamarine, and therefore how valuable it is? So the simple way that's done, sort of like diamonds, is you have a set of color squares of cut stones at the top, and you can see that they've got different grades. And as you get a darker color blue, they increase in value until you get to gem grade, which is Santa Maria, and almost nothing fits that category. So unless you go to a really fancy jeweler, you're never going to see anything more than a AA, or maybe if you're lucky, a AAA in a smaller stone. Now, this color grading is incredibly complicated. And so usually what happens is, if it's a stone of any significance, like size and reasonable color, it's sent off for grading to a place like the Gemological Institute of America. And there are a number of places that do grading like this. And you can see that instead of just those 5, the GIA has this huge chart. And right in the middle, not too light, not too dark, is gem quality. That's the Santa Maria, big arrow pointing at it. All that stuff off on the top, that's ugly as far as GIA is concerned. And all the stuff at the bottom can't possibly have any brilliance or sparkle, because you can't see through it. It's pointless. And so if you look on the right, you're looking at tone, which is another way of saying color, and saturation. the more saturation and the more color, you get to a certain point and the stuff isn't very good. But instead of just that one gem, if you look over here and I can figure out how to do it, that gem right there that my pointer is pointing at, this one up here, oh, I blew it already. It's the one up there. That one is the Santa Maria color, but all of these others are acceptable, even though you can't get Santa Maria prices. And so for really valuable colored gems, you get a specialized laboratory like Gem Wizard. And it's got automated instruments. You take your gem and you stick it with the flat surface down on a scanning instrument. And that scanning instrument looks at all of these different pixels across the face of that gem and assigns a digital color to them, just like you can do on your computer at home. And it gets this full picture of every single part of that gem down to the gnat's ass. And it produces a report like the one at the lower left. And eventually it says the stone is average. And it's a medium light blue. And it's got moderately strong color. That's the saturation. And it really still has a tint of green in the blue, which is actually a good thing because that says it hasn't been heated. And for some connoisseurs, especially of large gems, they want it to be a natural stone. They don't want the color to be enhanced by radiation, and they don't want the color to be changed by heating. Even though heating in particular is an acceptable process for most gems, including things like aquamarine. Anyhow, on to the next beast. The green stone of the Greeks, emerald. Everybody knows about emeralds, and everybody knows that emeralds were Cleopatra's favorite gem. Well, in fact, that's wrong. Cleopatra's emeralds, like her famous emerald necklace, the stones in it are actually peridot. And that's because when people decided that emeralds were Cleo's favorite gem, every green stone with a really good green color was an emerald because they didn't know how to tell them apart. And so that's an object lesson. Lots of stones have the same color. You really can't tell what stone you're getting just by looking at the color. And that's why those defects, the inclusions, can become important, because it's actually very easy to tell the difference between an emerald and a peridot by looking at it through a loupe. Emeralds are the exception to the beryl family. They almost always are included. They have defects in them, not cracks and things like that. That's bad. But they usually have so many inclusions in them that the inclusions have a name. It's called jardin, Gardin, the garden. And you expect to see that in a natural emerald. And so if you look at an emerald through a loupe and you don't see that, it's either synthetic or the defects in it on the surface were filled in, sometimes with glass that's ground up and stuck into the cracks under pressure. All sorts of tricks, especially in places like Thailand, where lots and lots of gems come from. Not because they're native to the ground, but because the Thais are really good cutters. And so lots of colored gems are sent to them, and they're famous for treating those gems in ways that are not quite kosher. In any event, you can see a gem crystal on the left, and the largest crystals are not very big because usually the inclusions and the cracks are terrible in one of these crystals. So by the time you find even a decent one that has uniform color and not too many inclusions, you're down to very, very small crystals to be cut. And so the largest decent crystal is about 7,000 carats, which isn't very big compared to those giant beryls or aquamarines we were talking about. And the largest cut gemstones, the two on the bottom, are only about 200 carats. So you've got Theodora that was discovered in 2001, and that's when it was cut. It's almost 60,000 carats, weighs 25 pounds, but it's opaque. It's cut anyhow because something that size with such uniform color is very unusual. But what you want is the best of the best, and that's the imperial. 206 carats, and you can't see any inclusions except with a really high-powered loop, but there's nothing visible to the naked eye. And it's called the Imperial, and it's owned by the Baco Company, and it's got its own website. So really famous gems, are really famous, like the Hope Diamond, the best blue diamond in the world, and the biggest one that's in the Smithsonian. But it's really owned by Harry Winston. Different story. Anyhow, there's another one that's slightly bigger called the Mogul, but it's not as good. It's not as clean, transparent. So the Imperial is the creme de la creme. Now, there's a weird kind of emerald that most people have never heard of called Trapezie emeralds. And they were described from the most famous emerald mine in Colombia, the Muzo mine. And the Muzo mine produces what are called the best emeralds. And it was in production when the Spaniards found the mine, and it's still in production. So it's been going strong for something over 400 years, at least. And the Incas and other Native Indians in the Columbia region or around the Columbia region knew about emeralds and used emeralds for decoration. And so who knows how long that Muzo mine has been in production. Anyhow, these weird emeralds were first found in the Muzo mine, and now they've been found in a couple of other mines in the region. The strange name Trapezie comes from the Spanish for sugar mill. And Trapezie emeralds, when they're cut well, and this is all due to the cutter, because you get one of these weird looking crystals like we saw before, and somehow the cutter has to figure out what's the top. And then he has to figure out how to cut this three-dimensional stone so that this wagon wheel shape shows up. And you can see that there are all sorts of different Trapezie emeralds that are shown over on the bottom left. And most of them, including the ones in my collection, look like that middle one. They're totally included. They're not very green, but they show the wagon wheel, which is really the important aspect of the Trapezie. And it turns out that the Trapezies actually have parts that make sense. They've got a core. Sometimes it's invisible or very small. And then there are prisms of emerald that grow up on the sides of those cores. And then those arms are actually made up of organics, carbonaceous materials. And the wagon wheel pattern reflects the hexagonal symmetry of the beryl itself. So as those prisms grow, they clean out all of the impurities and concentrate them along one of the faces. And that's what ends up producing the wagon wheel shape. They're under intensive study, and we still have no clue how they're formed. Lots of ideas, no proof. And the largest gem is 56 carats, but it's ugly as hell. Anyhow, more types of beryl. There's something called noble or green beryl, and it's not a pale emerald because it doesn't have any chromium or vanadium in it, which is what gives the color to an emerald. So it's yellow to greenish blue, and it's got both ferric and ferrous iron in it. And people don't like the yellow color. People usually don't like yellow gems. So it's usually heated to remove the yellow. And the largest gemstones are pretty big as far as, now we got to go back to being a clean crystal again. Transparent, no defects before we can cut a good one. So it's seldom cut into a gem for some reason because people think that's a bad emerald. And it's really not. And it's actually one of my favorite stones. I've got some absolute beauts in my collection. I absolutely love them because unlike emeralds, they sparkle like crazy. And they sparkle unlike other green stones as well, which makes them really special. All right. Having said people don't like yellow gems, there are two kinds of beryl. Heliodor and yellow or golden beryl, and they were both found at about the same time. And because of that, people think they're the same thing, and their names are used interchangeably. So if you go looking for a yellow beryl, you're likely to see that it's called Heliodor, and vice versa. And because Heliodor is really rare compared to yellow beryl, it's really hard to find a good picture of a Heliodor that's been cut into a gem. And I've got some gems that I bought from reputable dealers who have told me that they had been tested and they really are Heliodors. And I hope they're right because the price differential is significant. In any event, ferric iron is the coloring agent, but yellow and especially golden beryl is often irradiated to produce or enhance that color. And the largest cut gemstones can be very large because they're basically can be produced by irradiating large crystals of a different beryl variety and wiping out the color components with radiation so that the only thing that shows up that's left is iron. And that's one of the trickier things about beryls. By irradiation, in the case, for example, of aquamarine, you can start out with a pink beryl, you can start out with a green beryl, you can start out with all sorts of colors and then irradiate them, and all of a sudden you end up with an aqua because you're producing color centers like that Maxix type. And so you have to be really, really careful when you buy an aqua, especially an expensive one, as far as knowing how it was produced and whether it's natural or not. In any event, I love Heliodor. The thing that sets Heliodor apart from the golden beryls, and I love golden beryls as well, is the fact that in addition to the ferric iron, they contain uranium as an impurity. And so they end up producing color centers, which gives them that funny tint. And they're radioactive, but you don't have to worry because it's alpha rays and they don't travel through the stone. So only the surface uranium produces a little radioactivity that you might get. So they're safe to wear and things like that. All right, here's another one that's even sketchier than the yellow beryl, and that's morganite. Discovered at the beginning of the century, originally called pink or rose beryl, but it actually comes in a whole range of colors from the light pink all the way to a beautiful peach. So a combination of pink and orange. And instead of being orange pink, it's pink orange, where the dominant color is the peach or is the orange, and the minor color is the pink. And if you start looking at colors, they're all broken up for most stones into primary and secondary colors like that. And so whether you call it orange pink or pink orange makes a huge difference when you start talking about how good the stone is. In any event, the primary coloring agent is manganese in the +3 oxidation state, but it almost always has color centers as well. And they're the ones that give it the orange tint. And so it's often irradiated to get rid of the orange and actually enhance the salmon or the pinkish color, so that you end up seeing some morganite that actually looks red because it's been over irradiated. And the problem is that if it gets too hot, although you're never going to get it above 500 C unless you stick it in an oven or something like that, the color can fade. And it's one of those included types of stones because of the impurities, so that even though the largest crystals can be over 50 pounds, the largest cut gem is only 115 carats. But it's a beautiful gem if it's the right color and it's cut right. And I have some peach colored morganites to die for. They're absolutely gorgeous because of how much sparkle you can put into them. Now we're getting to the weird ones that most people have never seen. There was a mineral that was discovered in 1904, and it was a funny formula that looked like beryl, but not quite. And it was red, they thought, but they didn't have crystals. And they finally found crystals over 50 years later in the Wawa Mountains of Utah. The problem is there's basically only one mine. It's owned by two brothers who hate each other. And so the production is extremely limited. And at this point, it's been discontinued. On top of that, in spite of the fact that we were talking about all of these beryls being produced in pegmatites, which is a form of granite and fairly easy to get rid of, these are embedded in rhyolite. So they were formed basically at the surface, in surface magma, not in pegmatites below the surface. And that rhyolite sticks like a son of a gun. So first of all, rhyolite is like granite, and it's tougher than all get out. And so the way they get to it is they blast the rhyolite. And that doesn't help crystal size very much. And then once you find an intact crystal, after you blasted the hell out of the rhyolite, you got to remove the rhyolite. And so what you end up with is really, really tiny crystals. It's a beautiful color. It's called gooseberry red. Now, I'm used to thinking of gooseberries as green because of what they looked like in the Midwest. And so maybe what I was collecting wasn't gooseberries. So I don't know, but that's a very weird way to describe the color. In any event, they're red. And it was originally called bixbyite because of the guy who found it. But there's another mineral called bixbyite with a Y. And so that didn't wash with the mineralogists. And so it was flipped over and it started to be called the red emerald. And then finally, the mineralogist and the gemologist got together and said it's red beryl. And that's what it's called. All right, so you can get a couple of gems of reasonable size, but most of the crystals, and therefore most of the gems, are much, much smaller than 1 carat when they're cut. And in fact, there are about 10 points where there's 100 points in a carat. And so that's 1/10 of a carat, a very, very small stone. And I've got some that go up to 20 points. And that's the biggest one in my collection, but they're real, they're not synthetic. That beautiful cut gem on the right is probably, at the very least, an enhanced red beryl, but more likely a synthetic one. And the difference is that the color in the natural ones is stable at high concentrate, at very high temperatures, but the synthetic ones are almost never stable at high temperatures. Now I'm getting back to the unit cell here. I'm almost done. And as I said, this is the structure. It's got channels down the middle, and those channels can trap metal ions. And so here we have a very strange variety of beryl. It was discovered in a pegmatite in Russia. And so the Russians said, aha, a new mineral. And they called it vorobayavite, God forbid. All right, and they realized that it was beryl with some of the beryllium ions replaced by cesium or sodium ions. But they don't have the same charge. And so in order for the gem to be neutral, it traps potassium and lithium in those channels to balance the charge of the stone. Now, it turns out that that's the same mineral still. It's just got a lot of impurities in it. And so it's a gem variety. And the way you would name it is beryl variety vorobayavite. And it's still not, nobody's still sure that it's a real thing. And so, because all you find are these little tiny crystals of it. And they're funny crystals. The ones from Russia look like squashed hexagon crystals. And if you look at the analysis, what you see is they've got lithium and sodium and potassium and cesium, and a lot of it, it's almost 10% by weight. That's a lot of impurity, but it's still an impurity. Now, the stuff that was found in Afghanistan and also in Italy was given a different name. It was called rosterite. Rosterite, yeah, rosterite. And it has a slightly different analysis than the vorobayavite. And supposedly comes in these really dark crystals, even though the analysis is not that different. And so why these two forms should be the same mineral is up for debate. On top of that, the Italians had to get in the act, and they found what they say is pink rosterite. And here's a sample of it, and it's grown as an inclusion in goshenite. All right, in colorless barrels, so you can see it. And given that all of these varieties should be colorless, allochromatic, what the hell's going on? And the answer is nobody's sure yet, which is not very satisfying. All right, and then you get to this guy. It was originally discovered in only 2002 as a new mineral. And it was called raspberry beryl for the obvious color of it. And it's got cesium and lithium substitutions as well, but it's got much, much larger amounts of cesium than the vorobiavite. It's got crystals that look sort of the same, but you can see that those aren't perfect hexagons. They're sort of cattywampus. And in fact, it's got a different structure than beryl itself. It's got trigonal symmetry instead of hexagonal symmetry. So it's a new mineral, even though it should be something similar to the vorobiavite. And it was finally given the name pozotaite. And in the beginning, cut gems were very much like those red beryl ones, little tiny things. And I was happier than a clam to get one that was, again, about 10 points. So a cut gem that's 1/10 of a carat, little tiny stone. And it's a very, very rare stone. It was originally thought to be the rarest gem there is. And now it's only one of the top 5 because 4 other ones, at least 3 of which are rarer, have been found in the last few years. Because remember, this was discovered in 2002. So all of this new mineral discovery activity is happening in the last 10 years. And nobody knows for sure what the trace impurities are that are giving it color, but they've got to be there because, again, it should be allochromatic. None of the cesium and lithium should make any difference, even though the structure has gone a little cockeyed. And then we get beryl-like minerals. All right, and so you've got basite, which is this blue crystal at the bottom left. Now, all of the aluminum in the beryl has been replaced by scandium. And it was first found in 1915. And it has the same structure as beryl. It still makes long hexagonal crystals. But it's got a different formula, so it's a new mineral. And again, it should be allochromatic, but people think the color is due to trace ferric iron. And again, it's such a rare mineral, and such small quantities of it pure have been found that it's almost impossible to analyze it, even with modern micro inorganic techniques. But they're getting closer and better at it. And then there's staubenite, or staubenite, I guess it's really, and that's the crystal in the middle. And in this case, all of the aluminum has been totally replaced by ferric iron. And so it's idiochromatic. It should have the color of ferric iron, which is usually yellow, but it has these very pale blue hexagonal crystals. It's almost colorless. And again, people don't know exactly why, but it's isostructural, same structure as beryl, but a different formula, so a new mineral. And then very recently, another one has finally been analyzed to figure out what it is. And it's indiolite, because it was found in India. And it's this strange formula, but if you untangle it, what you realize is it's the same kind of formula that you find with beryl. But it's very strange. It was formed on the side of a volcano. So it's only formed at high temperatures in rapidly cooled magma. And because it doesn't really have a formula that fits or a structure that fits, even though the crystals look like beryl, it's placed in what's called the beryl group. So beryl can be the name of a whole bunch of minerals that don't have the same formula and don't quite, and or don't have the same structure, but they're close. All right, so now the last bit, the tour. I have a friend named John Rhodes, who is a gemologist and a master cutter. He cuts some of the best and rarest gems in the world and has a fantastic website, although he's trying to retire. He's a few years, I think he's about, maybe as much as 15 years younger than me. But he is a prospector. In addition to being a gem cutter and a gemologist, he goes all over the world prospecting for what's called rough, the stuff that you find crystals in that you can eventually turn into gems. And because he's a master cutter, he can take what he finds and turn it into a gem and cut out all the middlemen, which is why I love working with him, because his prices for even some of the rarest stones or the best cut stones around are reasonable. And I've known him since I started gem collecting. In any event, he used to have something called a gem retreat at his house in the town of Salida, Colorado. And it's near a really high mountain called Mount Antero, which is that thing sticking up, and is really sort of a mountain rangy type thing. And it's the source of the finest aquamarine in North America for over a century. So I was there, and John said, "You want to go on an expedition?" And I said, "Of course." Little did I know, I was in my early 70s, but still hadn't gone through all of my structural damage except for the one I had around 50. And so I thought I was up to this. And the bottom line is, this is the top of a very steep mountain. And at the very top, under the bottom of that rock formation at the very peak, is where the claim is that we were going to see. And it's just below the rocks at an altitude of about 13,500 feet. All right, so it's at an altitude where you're puffing if you move, let alone if you climb. And even worse, to get there, we had to take one of the most terrifying 7-mile rides in a Jeep that I have ever had. And I have ridden in Jeeps all over the mountains in New Mexico. And this one took the cake. It was scary as hell. We were on the side of a road, an unpaved road with big rocks, and it cut into the side of a mountain, basically, all the way up. And it was so bad that on the way down, the Jeep broke an axle. Fortunately, we had 2 Jeeps, and everybody piled into one Jeep that should have held about 5 people and suddenly was holding 10. Very exciting. In any event, you get to the bottom of the cliff and you hike 2.5 miles to the right bottom along this big rocky jumble, giant boulders like the stuff you see on the very bottom. And then basically you climb almost straight up the last 400 feet. And all this stuff is loose scree. That says if you're not careful, you take 1 step forward and slide 2 steps back. All right, so now we're on the claim, and the views, as you might expect, are absolutely spectacular. In any direction you look, you see something like this. Absolutely amazing. All right, so the claim owner and his helper, and the guy on the far left with the stuff on the ground is my friend John. The other guy that is the owner of the claim in the white hat in the middle here, and his 2 helpers one of whom is a circus performer who was taking a sabbatical, the summer off, to work with this guy on his claim because it was good exercise and he didn't like going to the gym. So this was the way he stayed in shape for doing his aerobatics. He was a trapeze artist of all things. And I can't remember what the other guy was, but he was something very strange. And this was his summer job as well. But they had spent 2 mining seasons, which are about, at this altitude, sometime around 3 months long. And they had managed to cut this flat spot, a shelf, into that bottom of that rock formation that we were looking at. But it took them basically 2 years. And so we got to the claim at exactly the right point. They were now ready to actually prospect for aquamarine. And so here is the bottom of that cliff. And down here where John and the owner are lying down and looking at the cliff is where they thought should be a pegmatite pocket, a little one. And so my job was to go up onto the top of this thing, and you can see this round hole over here. And so I spent hours digging a pit about 2 feet deep into this stuff. It looks like sand, but it's rock. Soft rock, but rock. So you got to sit there and bang on it with a hammer and chisel. And on the way down to the bottom, I found a few small aqua crystals. And that got the owner really excited because that was a clue that this really probably was a pegmatite pocket. And so he started digging into the side of this hump that was on the back of the shelf to intercept from that side where he thought the big pocket really was. And by the time he was done, the hole was so deep that when he crawled into it, all you could see were his feet. Now, he's under 6 feet tall, but still digging a hole big enough for him to crawl into 6 feet deep is quite a job. And he did that while I was resting, thank God. And remember, we're doing this at over 13,000 feet. Not much air. Now, this is my aqua find, the best one. I found some smaller crystals, but that's the aqua I found, and it's over 30 carats. But it's really not gem quality. But the owner was right, and there was a pegmatite pocket when he got done digging into the side, and he found several large, clean, very dark blue crystals that in total weighed over about 2,000 carats, which is a lot because all of the stuff was pretty much gem quality. And so that haul was probably worth on the order of $50,000. And that was for 3 short summer seasons with 2 helpers and me and John. Anyhow, this is looking back down that scree field, and you can see way up at the top is where the miners are still working. And I took this picture from the bottom of the cliff after I slipped on the way down and caught myself with my arm over my head, literally my whole weight on that one arm grabbing onto a rock on the way down. John and his friend were smarter than that, and they came down the side, which was less slippery. But I didn't have, I was the first one down, and so I didn't have anybody to watch. They saw me fall, so they went over to the side, even though it's harder to do. In any event, those guys were still hard at work. And remember, they had to come back down and go to a camp, so they didn't have to hike in, although their camp was basically where we left the Jeep 2.5 miles that away. Anyhow, that's the end of it. And questions, comments? Is anybody still with us?
Few of us.
Yeah, I've suddenly lost the screen I'm looking for. All right. So all of a sudden I can't see me, and that doesn't do it. So I don't know what I did, but it wasn't good. Oh, maybe over here. Hang on for a second. I'm looking for something that says full screen and I can't find it. Oh, there it is.
You have to move it. Yeah.
Come on, you damn thing. You showed up for a second and then you disappeared. View. No, that's not it. Sort. All right, I give up. I don't know where my screen went, but I can see everybody. So, and if anybody's still with us and has questions, I'll be happy to answer them.
Thank you, Steve. Francher here.
You have a question, Francher?
Presentation.
No, just want to thank you. Thank you very much.
My pleasure.
Yeah, it's good. Good information.
Yeah, well, a lot longer than I expected, but as usual, every time I have a slide, there's a lot I can say about it. As much as I try to minimize the words on a slide, and I covered a lot of subjects, but in order to really understand what varieties of a mineral are that are gem quality and why, all of that background is important, because you can see why gem minerals for the most part are rare, because they have to be formed in that concentrated mix of ions that ends up in the middle of those pegmatite pockets. And the rare earths in particular are found in those kinds of pegmatite pockets. There are exceptions, but a lot of the ones that are used in things like television screens and for all kinds of electronic devices are found in those pockets. And the way they find those pockets is by looking for those seams that end up getting exposed because the ground or the rock above the seam gets weathered away over thousands of years or tens or hundreds of thousands of years, and a little bit of it gets exposed, like at the top of the mountain that I showed you. And you have to sort of guess where the pocket is for the most part, because unlike those gymongous ones that I showed in the picture, most of the time you're looking for a pocket that's a really small one, like we found up at the top of Mount Antero. Now, we found a little one because most of the big pockets are either being mined commercially, and so there's heavy equipment, and other parts of the top of that mountain that I was on. If you can believe that somebody manages to build a road, a zigzag road up the side of that, and brings in something like a skip loader, one of those things that's sort of a mini steam shovel or what, with a little bucket on the end of it. And they can actually use that for commercial mining, and then they look for crystals in what they dig up. And so they've got a system for bringing the ore down and sorting it and all that kind of stuff. And then other pockets are just like the claim owner that I worked with. They're small and privately owned, but the people that own them protect them for all they're worth. We ran into one family at the base of the cliff that owned one of those pockets, and they basically mined it almost 10 months of the year. So they were up there as a family digging into that pocket and finding crystals and selling them. And that was their only source of income. And so, especially in a place like Colorado, there are a lot of independent prospectors who do that kind of thing. And we ran into one really nasty group that wasn't commercial, but wasn't just a family. And they had guns, and they didn't even like us walking along the base of that cliff past their claim. Even though their claim was up at the top, you know, they yelled down at us, "What are you doing here?" kind of thing. And, you know, these little tiny holes in the ground all over the world are where most of the gems come from. You know, places like India and Pakistan, all kinds of barrels come from there. Barrels are very common. They're found all over the world. And so there are people digging for pegmatite all over the world, just like we were doing. The economics of gemstone trade, from the guys who dig to the guys who cut to the guys who sell, you know, that gem changes hands many, many times along the way because each person has a different job. And that's one of the things that contributes to this cost of even a small gem. Because even though a lot of labor is done in a third world country by people who are paid pennies, maybe $1 a week in some cases, like, or something like that. You know, by the time you get to the last guy, they're still expensive. So it's, you know, and I barely touched on the subject of color. I could talk just about color and the transition metals and ligand field effects and all of this other kind of stuff. That's an hour lecture, at least. And I've given those kinds of lectures, and I've given parts of those kinds of lectures to the wanderers before. I think altogether I've given, starting in 2004, 7 basic lectures to the wanderers. And I have, now that you've got this background on silicate gems and where they come from, I have some pretty much prepared gem talks about other gem minerals like zircon or like tourmaline or like garnet. And you have the background to understand any of those talks now that you've suffered through this one. So anytime Don or the group wants me to resurrect one of those and update it a little bit, I'll be happy to give one.
Okay.
Like, pick your favorite gemstone.
I'm assuming that when you gave these talks in person that you had samples with you.
Oh yeah, that was one of the things that made the talk long enough or different enough. And I would bring a box of aquamarine, or I would bring a box of emeralds that I have in my collection. That emerald is found in Brazil, but it's found in lots of other countries as well. And so one of the things I like to do, because the impurities in an emerald from a different country is different for each of the countries, I like to collect samples from all of those countries. And I have a very crude, but a very effective gemology laboratory with all of the instruments. A lot of them, you know, tabletop or handheld, very simple. They don't require any electricity or anything like that. But I can do almost all of the tests required to identify all but the rarest of the rare gems. And I have gemology friends, in particular, a lady who's a consulting gemologist who does that for a living in Princeton, New Jersey. And because of my connection through cutters that I buy from, and that I meet who come to shows and things like that, I had until I stopped collecting, which I stopped collecting about 5 years ago. When my income dropped, I decided I wasn't going to consult anymore. And so I wasn't going to spend any money on gems. And I started buying plants for my backyard instead. A lot cheaper and a lot easier to see than all of the boxes I have. But I have a closet full of boxes with gems individually sorted, labeled, weighed, and measured, and stuck in a little jar under plastic so you can see it without touching it.
Again, I thank you, Steve. I'm going to have to leave you, boys and girls.
I appreciate
Yeah.
you sticking around for this long. Trancher,
Oh,
always good to
I'm
see
sorry
you.
I was late.
Yeah, I've got to do that too.
No problem. Well, again, it's past my bedtime. It looks like it's what, 9 o'clock?
Just about. So if anybody's
Yeah.
interested, the reason I'm leaving is that David Attenborough is giving his climate catastrophe talk starting at 9 on PBS.
Ah,
Oh,
Actually, it started at 8.
well,
Okay.
it did.
Good night,
Uh-oh.
everyone. Good night.
I hope you recorded it. Anyhow, I'm going to take my leave as well if I can figure out how to sign off.
Just hit leave.
Well, I don't
So,
have that button showing because the screen is missing.
Oh,
So I don't know what I did, but I
You
don't
can
want to
just-
do it anymore.
so
Stop
I
sharing.
think you'll be
Oh,
okay.
there we go. I found it. I'm in
So
business.
you're going to do the next stage of the
Right,
the,
right.
uh,
Yeah. Again,
back
I
yeah, or
actually,
back.
because this talk, the slides for this talk were partially made, and I sort of cobbled them together from a
Mhm.
number of the other talks that I've given over the years,
Mhm.
and then just updated those or modified them. I actually did a little work on the talk that I'm supposed to give on the 7th. And that talk is
Okay.
going to be a continuation of the perception talk on interoception, and in particular on proprioception, the part of interoception associated with movement, how we control our bodies and how we can control our bodies. And then if there's time, I'm going to talk about the sympathetic nervous system and all of the receptors associated with it.
Okay.
And I've pretty much got that talk organized. It's just a matter of
Okay.
leaving out some of the more complicated slides that I really don't have to
Yeah.
show in order to make sense of it all.
Yeah. Okay.
All right, so for those of you who are gluttons for punishment, I am going to talk again next week on part 2 of perception. And with that, I bid you all adieu.
I do. Lynn, would you send me Todd Duncan's email contact or address?
yes, I think I have. But I've got all the information. He sent me a Facebook message.
Just text it to me if you will.
I can copy and paste it. And do you prefer email or you had a
Email would
different
be
name
best,
on your
yeah.
email. I was kind of curious about that.
What's that?
You had a different name on your email? It wasn't
Langdon?
began with an L.
Yeah, that's my name. Langdon.
Oh, where'd that come from?
Uh,
All these years and I never knew.
well, it's I don't use it very much. I just use the last 3 letters.
Hmm.
Don. Yeah.
Well, this is the first time I'm finally able to use my Chromebook. I'm not
Oh.
quite sure how to get it to work right, but I'm
Yeah.
trying.
Well, you got a good start and you got it unblocked, I guess. Huh?
So, well, I was due to using a computer at my mother's independent living facility in Albany, New York. Somehow my account and
Hmm.
a person named Sassy Sky's
Mhm.
account got synced on Chrome.
Huh. Huh.
But my son finally figured out how to get rid of it. And it was so simple that I was able to mostly do it myself.
Great. Good going. Okay. Good night.
The powers that be did not know.
Yeah.
So anyways, I will text or email
Sounds
you.
good.
Is that what you want?
Sure.
Email,
Yeah, that's fine.
etc.
Okay.
And
Good
I'll
night, Ron. Wake up.
copy him too. Thanks for hosting.